we had the notion of a subspace in Rn, and now again, as we've done with spanning sets and linear combinations and things like this, and linear independence, we want to build this notion to the setting of an arbitrary vector space. So let's let V be some arbitrary vector space here. So let's say V, and this is an arbitrary vector space. And then let's say contained in V is a subset W. So right now, this will just be a subset right? Remember, a subset is something that for all x in W, that implies x is also an element of the vector space V, right? Now, this is just a subset. We're not guaranteeing that it is a subspace. And what is it? What do we have to show holds to guarantee that it's a subspace, right? Well, we have the following definition, which I'll now generalize, is if for every x and y in W, this implies that for scalars a, b, and the reals, we also have that ax plus by is an element of W, right? If this holds, then we say W is a subspace of V. So it's a subset that follows these special properties, right? Or that meets this criteria right here, is that linear combinations of elements of your subset are also in your subset. Well, then it's kind of upgraded to a subspace, right? So let's prove the following theorem that involves classifying subspaces. So we have that W contained in V is a subspace. Subspace. If and only if W is a vector space. And let's say with respect to plus sub V and then product sub V, right? Where here, when I write like plus sub V and product sub V, this means with respect to the addition and scalar multiplication operations that have been defined on the larger vector space V here, right? And so here's the claim, is that W is a subspace if and only if it itself is a vector space. So let's prove this. And let's go in the forward direction, right? And the forward direction means we assume that W is a subspace, right? And then we need to show that W is also a vector space. Sorry, I lost the word space in here, right? W is a vector space. What do we need to show then? To show that W is a vector space, we need to run through all the axioms of addition and scalar multiplication. Well, if W is already a subspace, this implies that every element of W is an element of V. And if it's an element of V, well, then it satisfies all of the axioms. This implies for all x in W, x is also an element of V, which implies the plus and scalar multiplication axioms hold. Let's say the algebraic ones, right? Like commutativity, associativity, distributive property, these things. So let's say the algebraic axioms hold kind of just by definition. By definition of subspace. subspace, right? Because if V is a vector space, well then we know these axioms hold for every point or pair of points x and y and v. Well, then certainly it holds in some subset of those points, right? What haven't we shown though here, right? We have not shown the existence of an inverse and identity element for addition, right? However, we do know that, so we need to show the additive identity and inverse exist in W, right? Because we're looking, here's V, we're looking at some subset W or some subspace. Why could we not have that, the identity element here, 0? Why could we not have that that's some other point, right? Not necessarily contained in V. Or, maybe here's V, but the additive inverse negative V is out here or something. Why can't we have that? Well, let's see why. We have here, we have that our algebraic axioms are satisfied, which means if we have V in W, this implies, or let's use X. X in W, this implies AX is an element of W for all A in R, right? This is one of the axioms of scalar multiplication, well, is that it's closed under scalar multiplication. And we know that it is because points in V are closed under scalar multiplication, and points in W are also points in V. So we're closed under scalar multiplication. Well, then take A to be 0. We've proven for an arbitrary vector space that 0x equals 0, which implies that 0 is an element of our vector space. And then we can also take A to be -1, which we've also proven that -1 times x is -x, which implies that -x is an element of V for all x. W, my bad. For all x and W. And so now this completes a proof that if W is a subspace, then it's necessarily a vector space, right? Because we've now shown that all the algebraic axioms hold. We've shown the existence of an identity and an inverse, right? And so this implies that W is a vector space. Great. Now what do we need to do? Now we need to prove the opposite direction, right? We've proven, or we've started with the assumption that W is a subspace and proven that W is a vector space. Well, now let's start with the assumption that W is a vector space. And again, this is with respect to the operations plus and scalar multiplication defined on V, right? So if W is a vector space, well, this means we satisfy that. In particular, it means we satisfy the elements of W are closed under vector addition. So this means if you have X and Y in W, this implies X plus Y is an element of W, right? We also have that we're closed under scalar multiplication. So if you had like AX in W, this implies that, oh, sorry. How about if we just have X in W? This implies that for all A in R, AX is in W, right? That's a much better statement. We have the same thing, right? We can restate that for a different element Y. This means for all B in R, BY is an element of W. So how do we take all of this information? Right, again, we're using what properties here? This property is that vector addition is closed. And these two properties here these implications are because scalar multiplication is closed. And these are assumptions we're making because we know that W is a vector space. We're allowed to assume those axioms, right? Well, then let's take all of this information and put it together. Now, what do we have? We have that if X is an element of W and Y is an element of W, well, then we know that AX, we know that AX and BY are elements of W. And if AX and BY are elements of W, well, then their sum is also in W. So we have for all X, Y in W, this implies that AX plus BY is an element of W. And this is precisely what it means, or what we need to show for a subset of a vector space to be a subspace, right? That's exactly what we needed to show. So this implies that W contained in V is a subspace, QED. So subspaces of vector spaces are those that are also a vector space on their own, right? So if you have some subset of V, but it is not a vector space on its own, well, then it's not a subspace. It's just a subset, right? Okay. What is a corollary we have to this theorem here? We have the following corollary. If you'll remember when we were talking about, just in the context of Rn, we learned that subspaces were those, let's say W is a subspace of V if and only if there exists a set of vectors such that it is the span of those vectors. Well, we have that here. And now we have that if, then this means W is equal to the span of some collection of vectors, V1 through Vn, then W is a subspace of V, right? And why is this true? Well, this follows immediately from this previous theorem. What is a spanning set? A spanning set is defined to be the linear combinations of elements V1 through Vn here, right? So it satisfies the subspace criteria almost by definition, right? Because it's defined to be, W as defined as a spanning set. That would be like vectors W such that W is equal to like A1, V1 plus blah, 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 plus AN, VN, right? And so the elements are linear combinations of these vectors V1 through Vn by definition, which we've now seen in the previous argument makes this a subspace. So we have this relationship, but there is an easier check, right? Instead of running through, say, oh, well, to find if something is a subspace, all I need to do is find if it's a vector space. Well, finding that something is a vector space can be quite tedious, right? There's a lot of axioms to check and verify. We have the following subspace test that makes our lives a little bit easier when it comes to figuring out if a given subset is indeed a subspace. So let's let W be a subset of V. So this is a subset of vector space V. Then W is a subspace if all of the following hold. So there are three properties, and if all of them hold, then we can conclude that W is a subspace. The first one is that 0 is an element of W, right? So we need to show W contains the additive identity of V, right? That's one thing we need to show. We also need to show that for any two elements, W1, W2, and W, This implies that their sum is in W. And then we need to show also that for every W1 in W, this implies that for all A in R, we have that A W1 is also in W, okay? And so really the subspace test can be remembered much more quickly is you ask yourself 3 questions. And then you check those 3, and if all 3 of them are true, then you're done, right? You ask, is 0 an element of W, question mark? You ask, is W closed under addition, question mark? And you ask, is W closed under scalar multiplication, question mark, right? That's really what you have to ask yourself. And if you can prove these 3 things, or show these 3 things, then you've proven that this given collection, or this given subset of V is a subspace. So let's do an example. Let's show that W contained in P2, and remember P2, I'll write out what this is really quickly. Oh, maybe I'll do it over here. P2 is the set of at most degree 2 polynomials, right? So like ax squared plus bx plus c, such that a, b, and c are all real numbers. Okay, so let's show that W, where W is given by polynomials that have 1 as a root. Let's show that W is a subspace of P2. Now, to show that it's a subspace, we need to ask, does this contain the identity element? Is it closed under addition? Is it closed under scalar multiplication, right? We have to ask ourselves those 3 things. Now, to do that, we need to understand W a little more explicitly. W is going to be those polynomials, let's say P of X, which, and we can still write them as AX squared plus BX plus C, such that P of 1 equals 0, right? This is precisely what it means to have. When you say that polynomials that have 1 as a root, that means when you plug in 1 to the polynomial, you get 0, right? So what do we need to show? We need to show, well, we need to ask ourselves, is 0 an element of W? Well, let's take the 0 polynomial, which is just 0x squared plus 0x plus 0, right? Or just 0. Well, then what's 0 of 1? Well, that's equal to 0, which implies that 0 of x is an element of W. So we're good, right? We've shown that this set contains the identity element, or the additive identity element. The second thing we need to check is that it's closed under, excuse me, we need to check that it's closed under addition. So that means let's let P and Q, let's let these 2 polynomials be elements of W. Well, this implies that P of 1 equals 0 and Q of 1 equals 0. And now we need to look at their sum, right? What is P of X plus Q of X? Is this an element of W, right? That's what we need to ask. Well, let's define this sum to be R of X, and then let's look at R of X. Or let's look at R of 1, right? Well, that's defined to be P of 1 plus Q of 1, which is equal, P of 1, 1 is a root of P because it's in W. 1 is a root of Q since it's in W, so we get 0 plus 0, which is 0, which implies that R of X, which is equal to P of X plus Q of X, is indeed an element of W. So we've shown that it's closed under addition. Now let's see if it's closed under scalar multiplication. So let's consider for all A and R, let's consider A times P of X. And we have to ask ourselves, is this an element of W? Well, let's take A times P of 1, right? This is equal to A times 0, which is equal to 0, which implies that if you have 1 as a root of P, then 1 is a root of AP, right? So this implies that APX is an element of W. So this means it contains the identity element. We've seen it's closed under addition and closed under scalar multiplication. Therefore, W contained in P2 is a subspace. Cool. All right, I think I'm going to break here. And then what we're going to do next is we're going to, now that we've looked at subspaces again, now let's look at a basis of a vector space or a basis of a subspace, right? That's kind of where we went when we were looking in the context of Euclidean space. Now let's look at the context or the definition of a basis in an arbitrary vector space.